as a visionary technologist, I'm always looking for new sources of inspiration. Like many other visionary technologists, I draw a lot of my ideas from science fiction. Now, it's no secret that Star Trek's tricorders and datapads were major influences on today's smartphones. And likewise, the replicators have very inspirational for 3D printers and to, I think, a lesser extent, the Juicero. If we can bring all of these into the world, surely faster than light travel and fully automated luxury space communism must be right around the corner. But today I want to show you a different piece of science fiction that has inspired me. Yeah, the world of Clueless is that's the science fiction world I want to make real. I mean, it's a world much like ours. I mean, Paul Rudd even looks exactly the same. But you know, I want to help bring this vision into existence by recreating Cher's Closet in JavaScript. Essentially, what I built is it's a database with a recommendation engine. It's a little bit like Netflix's Top Picks or Spotify's Discover Weekly. That said, I hope it's a little better than Netflix because all I ever watch on Netflix are shows about animals that are friends, and I don't know why they're still trying to get me to watch goddamn Riverdale. There's essentially two parts to a recommendation system. You know, first you collect a bunch of data, in Netflix's case, the information about all the movies and TV shows in their library, who's watched them and how they rated them. And then you throw out almost all of it, all the movies that don't have a strong correlation to your tastes. You take a big data set and focus it down to the tiny bit that matters. Now, this describes a lot of things that we do with computers, right? I mean, a recommendation system is really just a sophisticated database, right? I mean, we query a database to focus on the information that we care about. But I think it's broader than that. I think there's a lot of things that we do in computation that are sort of in that mold, like regular expressions, for example. Regular expressions let you take a block of text and then find just the substrings that match. It's not the same as a database. I mean, a database is like designed to be queried, whereas you use a regular expression on freeform texts that are you sort of like hope conform to some sort of pattern. But both database queries and regular expressions are systems for extracting small bits of data from larger collections. And when I zoom out a bit more, I start seeing my career in these terms. Now, for the last, I guess, like 3 years now, I've been mostly building reports and data visualizations. So, like, the back-end engineers wield exotic time series databases to count every time you so much as fart in the presence of a Facebook ad. Then I query a teensy-weensy bit of that data and pour some D3 on it. Or, I guess, in like thought leader terms, it's not big data, but big meaning. This isn't. You know, okay, so I actually thought that this was a Shingy quote, but it is an Alan Kay quote, so you have to take it seriously. So I've come to see my work as a programmer not only in terms of what I build, but also like what I throw away, what I discard. Like there's infinite possibilities in the data that I'm working with. But as Max Kreminski puts it, programming is about gradually whittling away at the entire vast possibility space of general-purpose computation, roughly speaking, anything a computer can do, until your program doesn't do anything you don't want. And this is kind of the approach I took when I was building Cher's Closet. I mean, first I'm building this data set of all my clothes, all the facts about my clothes, and then I'm adding these rules of fashion, which are like the constraints that limit the countless permutations of clothes into the handful of outfits that make sense. So here's some of the wardrobe I'm going to be matching against in my system. I mean, I admit it's a bit less exciting than like that yellow plaid outfit. Masculinity is a prison. And this is how we might structure this data in like a JavaScript object. You have this data, the data associated with the term, like the article of clothing, the color, the seasons. These are just like properties on an object. If we were going to store this in a relational database like MySQL or Postgres, we'd represent maybe like each item is a row in the table with like additional joins to manage like the weirder like many-to-many relationships. But we can also represent this information as a collection of independent but interrelated facts. Like each property on the object or each cell in the table is a fact about the item that it's describing. More specifically, it's a fact about a relationship between the item and the property. So we might read this as in plain English as the flannel is a shirt. The sentence it describes the relationship between the flannel and I guess sort of like the abstract concept of a shirt. And this is sort of like the idea at the core of graph databases. When we talk about a thing having various properties, we mean that there is a subject-object relationship between the thing and those properties. So in my diagrams, I'm going to be representing these with arrows. And when I'm sort of like enumerating these relationships or querying the graph, I'll be using this notation here. Now, an item can have the same kind of relationship with multiple objects. We don't need anything like a join table to represent this. These are just like separate and independent facts. And likewise, this can go the other direction. Shirt can be the object of multiple relationships. So all of these data points, the close and their traits, they form a big graph. This is just like a subsection of it. I spent an enormous amount of time drawing little points, so I'm going to just like try and focus on the minimum possible cases here. Now, we can ask questions about this graph and its relationships. Like, for example, like what article of clothing is the flannel? We write the queries in the top left here is sort of like a fill-in-the-blank style. The uppercase X is a variable, so like for what values of X does this relationship exist? So how do we answer this? Well, we know where the flannel is. And we look for the article relationships that the flannel is. Here's the one we found. And so we have this article relationship between flannel and shirt, and therefore our result is X is shirt. And we can also query the graph in the opposite direction. We can learn about our relationships from the object's perspective. So we can ask, like, what items are shirts? So starting from shirt, we see it as 3 possible matches. Each one of these items can fill in the blank, so we return all 3 of them. Now something a little more complicated, like combining terms. So like we ask, like, what shirts are informal? Or in like the query language, we say, what item has a relationship to both shirt and informal? The same variable used in the clause, both clauses, that the X there, it means that the value will be the same. So let's iterate through the shirts again. So like white pattern is a shirt, but white pattern's only formality relationship is with formal. It doesn't match. But gray check, it has relationship with both formal and informal. It is both business and casual, so it can match, as does the flannel. So now I'm thinking, what are we going to do with this information? How do we form the outfits? My dear friends at Microsoft are probably squirming in their seats right now. It's like, oh, I know how you can do this. So the machine learning approach would be, looks something like this. So you start with training data. You have like a collection of known good outfits. You calculate the correlations between items. And like this style of jeans are more frequently worn with flannel shirts in these patterns. And then from these individual correlations, you derive rules for generating recommendations. For example, like given these pants and these shoes, the shirt options that most closely match the outfits in the training data. Now, I have a few problems with this approach, at least for me personally. Problem one is that I've just told you everything I know about machine learning, and I have 20 minutes to fill. Problem number two is that, like, at least this approach would require a lot of training data. I'd have to find a corpus of thousands of known good outfits. I'm sure that exists, but I don't know where to find it. And then the third problem, well, I mean, I guess I want to use an approach where I could really explain the decisions the computer was making, where the algorithm is like something that can actually fit on a slide, not like this mysterious force with which I'm trying to curry favor. So that's why I've decided to ignore the last 40 years of computing history. A lot of the AI research in the 60s and 70s and 80s used a technique called expert systems, where instead of processing a pile of data and then sort of deriving the inferences statistically, you have a domain expert formalize the rules and program them in directly. One of the best-known expert systems of the 70s was a program called Mycin, which diagnosed bacterial infections. Now, it would ask you a series of yes or no questions, which turn for roughly 30 minutes, and then bam, you have a diagnosis and suggested antibiotics for treatment. Now, Mycin was implemented as a Lisp program on Stanford's PDP-10, which is a machine much like this one pictured here. This was actually Microsoft's PDP-10 from the 70s. Now, the fundamentals of machine learning and neural networks, they were already well established by the time, but AI had actually already been through a boom and bust cycle by the mid-70s. They knew that you could do interesting things with machine learning, but the hardware was just not, ready. It was just impossibly limited for the kind of statistical analysis that we take for granted today. I mean, just to give some context, see this like turquoise refrigerator-sized thing here, that has about a megabyte of core memory in it, and the CPU, the thing with all the buttons on it, that could run through a little under 1 million instructions per second, which sounds really impressive until you consider that my wristwatch is several orders of magnitude faster. So for practical reasons, they skipped the whole learning part and put together a fairly small data set of around like 600 facts about bacteria and relationships between symptoms and disease and treatment. So my take on Cher's Closet works in much the same way, except instead of building my rule set over the course of many years with a team of medical professionals, I built it by, from tidbits I half remembered reading in an issue of Esquire many years ago. So these are the rules of fashion that I've implemented in my system. I mean, I only have so much space on the slide, so this may be a bit incomplete and simplified. I mean, these are really just like the rules I need to protect me from myself. So first is like pants and shoes should coordinate. You want khakis and other warm colors to go with brown shoes, cool colors to go with black shoes. Second, this is probably the biggest departure from the source materials. I want to sort of discourage matching shirts and pants. Like I have this rule in place because in my personal wardrobe, I have a lot of clothes that are like, I guess like the same color, but in different enough shades that it looks really weird when I mix them. And then finally, all clothes must be appropriate for the same like level of formality. I have this in place because I guess like one of my worst fashion habits is I'll wear like dress pants and a collared shirt and like really cheap sneakers I gotta pay less, which makes it's like the classic grandpa look, not very hip. So how are we going to implement these rules? We'll put together the first rule, so like matching pants and shoes. So these are the relevant relationships for pants, and then the relevant relationships for the shoes. So if we wanted to find two items with the same tone, we'd write a query like this, where X and Y both have a relationship to the same tone. Any two items that relate to the same tone would match. Note that I'm not specifying that one's shoes and one's pants, or even that they're separate items. I'm going to have other rules that specify this, so I don't want to over-specify this one specifically. We can take this query and then add it to the database as a rule in itself. And depending on how you look at this, this would be like analogous to a view or a stored procedure in a relational database. But what rules are really doing is they're creating dynamic relationships that you can query like any other. So in the case, X relates to Y if they relate to the same tone. So what this rule effectively creates is all these purple relationships on the right are added by this single rule. So the thing is, this makes diagramming all the relationships, even moderately complex system, unreasonable, so I'm just going to stop drawing diagrams. Anyways, now that we have this rule, we can use it in inquiries or in other rules. There's no limit to like how deep it can go. They can even be recursive, although I'm not using that in this talk. So putting this together with some of our other rules, we've got the matching tones, the non-matching colors. Note that we're explicitly saying here that the color associated with X does not match the color associated with Y. And then we put this together with the matching formality. This is a three-member relationship. I mean, I don't know how I would draw that as a diagram, but the computer doesn't care. And then this big rule here, this puts everything together. An outfit is a shirt, pants, and shoes, and they all coordinate with each other. So I can do a couple of different queries on this. If I fill in every parameter, it can tell me if they match or not. If I fill it in partially, it can tell me how to complete the set. And if I leave all of them blank, it will give me every single possible outfit. There's only like 10, so that may be why I have that sort of like cartoon character wardrobe. But I want to talk a little bit more about like the significance of this approach, of the significance of the approach I'm taking for this problem. So like the typical way that we think about problem solving in software, it's like following a sequence of steps, you know, the algorithm. Like the typical approach for finding matching outfits might look something like this. You just have these nested loops, and if you wanted to change the rules of outfit matching, you have to change the algorithm. So like, if I wanted to like add additional rules, I would probably like something in this if block here, I would like add more clauses to that. If I wanted to add more things to the algorithm, like jackets or like accessories, I'd have to add another layer of loops. And if I didn't want this to run in exponential time, I'd have to rewrite the whole thing from the ground up. I think what this does is it highlights a fundamental tension in software design, which is computer programs, we write them to do meaningful things, but computation itself is a process of meaningless symbol manipulation. A lot of the work that we do as programmers, it's really just translating between the human and the computational domains. Our job is encoding meaning into a computable form, then decoding it back out. And the processes we use for this, they intertwine, or they complect, if you're a closure person, the meaning and the computation. Looking at this, I'd have trouble saying exactly where the computation ends and the meaning begins. The only thing that I know that is definitely for us is the variable names themselves. Everything else, as far as I can tell, is for the computer. And with code like this, the real question is even like, how do I add a feature or how do I make it fast? It's how do I make this readable for computers and people simultaneously? But what if we could untangle the computation from the meaning? What if instead of writing an algorithm that performs the specific transformation I want on the data, we just create a graph of the dependencies in the data that describe the transformation we want, and then a general purpose algorithm, which is, in this case, a depth-first search with unification, that works with arbitrary queries and data. If I want to add new rules or new categories, the algorithm, the part on the right, that doesn't change at all. We're just adding more data. And if I wanted to solve a completely different problem, like, for example, this finds connections in a social network, the relationships are radically different, but the algorithm is still unchanged. Now, of course, this is not a new idea. All the way back in like 1958, there was an attempt to create a general problem solver. Now, this would be a daunting task, to say the least, with modern computers. In 1958, just to give you context, most computers were still running on vacuum tubes. The general problem solver was, of course, a failure, but less ambitious systems on more powerful computers followed. So like Myson, the program I was talking about earlier, this was one of its descendants. This follows in that tradition. And another example was there was in the early 70s there was a group of CS professors in Marseille working on natural language processing, and then there was they were corresponding with a group at the University of Edinburgh who were working on automated theorem provers, and they realized as they were talking about their approaches they realized they were actually solving the same problem. They realized that like their parsers and their theorem provers, and as well as like databases and constraint solvers, they were all really just graph traversal problems, and therefore they could be built with the same toolkit. And this toolkit ended up becoming the Prologue programming language. The language is actually the basis for my talk. So the notation on the left, that is actually Prologue code, and this on the right, this is a very limited but still functional Prologue interpreter. I think the interesting thing about approaching problem solving this way is that we have a new perspective on like how to frame problems. It's like the algorithmic-centric approach of imperative programming, it leads us to see solutions as necessarily like a sequence of steps. But this style of problem solving, for lack of a better term, I guess the declarative approach, it lets us see the problem all at once. It's like the difference between directions and having a map. Now, maps are not superior to directions. I mean, they just provide this different perspective and an additional way of looking at the problem. You know, a map helps you understand your trip in totality, but directions are what gets you there efficiently. And likewise, like a recipe, you wouldn't want a recipe that is just where you have to that is like a list of inferences between ingredients. It's important to have both the declarative side, which is this table of ingredients, and the imperative side, which is the list of directions. But if there's anything I'd like you all to take away from this talk, it's that although we will always have to write code, there is so much more our data could be doing for us, doing on our behalf. There's a few places where web developers do this already. I mean, I mentioned databases and regular expressions at the beginning of this talk, which are a perfect example, but I think for us, the canonical examples are HTML and CSS. I mean, you can tell that we are doing it right when gatekeeping jackasses say that it's not even real programming. But I think we can go bigger. I think we can change our relationship with how we build software. We can decenter the algorithm, invert the dependencies between meaning and computation. So I want you to think about how you could frame your problems not just as algorithms, but also as their relationships and as their constraints. I want you to think about how instead of translating your program's meaning into code, your code could accommodate the meaning expressed in a more humane form. And I want you to think about how you can approach your work not as building an artifact, but like finding a path through possibility space. All right, so I think that's enough of the thinking part. Let's look at the demo. Okay. Oh, this is never easy. Okay. Here we are. So, here it is. Here's some of my clothes. Let's try. It doesn't like that. Let's try. Here we go. All right, thank you very much.